Hey everyone, here's part 2 of rational functions from chapter 8 section 5 of your textbook. This one is going to be the longest of the 3 videos, and then we'll have a shorter video again tomorrow. But let's go ahead and get started and make sure you take notes on this video. You need to write down all the examples that I'm doing and take just really good notes. Cannot emphasize that enough. Okay, so let's look at f of x equals 1 over x minus 2 minus 3. So remember, we have this form, and this form is easy to figure out the transformations. We'd be going to the right 2 and down 3. So it's easy to do transformations, but let's look at it in a different form. First of all, from the equation, we know that since it moved to the right 2, that the vertical asymptote is going to be the set of all real numbers. I'm sorry, where x is equal to 2. Therefore, the domain would be the set of all real numbers. That's what I was leading towards, is the set of all real numbers where x is not equal to 2. And that makes sense, because if it were equal to 2, and I'd plug that in, if I had 2 minus 2, well, that's 0, and 1 over 0, that's undefined. Okay, and then for the horizontal asymptote, that's for the y values, and we've moved down 3, so that horizontal asymptote is at y equals negative 3. And the range will be this set of all real numbers where y is not equal to negative 3. So we know this much, but let's write f of x equals 1 over x minus 2 minus 3 with a common denominator on that negative 3. So if I have 1 over x minus 2, and I want this negative 3, which is currently over 1, I want it to have a common denominator of that x minus 2. So this is 1 over x minus 2. Then I have minus. Distribute that 3 to both parts. I'll get 3x minus 6, and then over x minus 2. So then whenever I collect like terms, I'll get f of x is now, so I have negative 3x, I have 1 minus a negative 6, so I have 1 plus 6, which is 7, so plus 7, all over that x minus 2. So don't forget we have to distribute that negative across there. Alright, so now we have this right here. It's the same function, just in a different form. So a couple of things to think about is what will make the denominator equal to 0. Well, if I take this x minus 2 and set it equal to 0 and solve for x, I would get x equals 2. So if I had an x value of 2, that would make my denominator 0. So because of that, I now know that my vertical asymptote is at x equals 2, and that means that my domain will be the set of all real numbers where x cannot be equal to 2. Of course, we already knew that from the other form, but say we didn't have that other form to begin with. We can figure out the vertical asymptote in the domain by setting the denominator equal to 0. So that's one thing that you need to take note of. Now, how do we get to the horizontal asymptote in the range? Because it's kind of difficult to see where are we moving up or down. So let's check out a table from page 594 in our textbook. So here's our table for horizontal asymptotes and rational functions. Let f of x equal p of x over q of x, like we just saw, where p and q are polynomial functions in standard form with no common factors other than 1, meaning it's been simplified as much as possible. The graph of f has at most one horizontal asymptote, so you'll either have one or none. So if the degree of p is greater than the degree of q, so if the exponent on top is bigger than the exponent on the bottom, there is no horizontal asymptote. If it is smaller on the top than it is on the bottom, then it is y equals 0. That is your horizontal asymptote. If they have the same exponent, if they have the same degree, then to figure out the horizontal asymptote, that'll be y equals, and you take the leading coefficient of p and divide it by the leading coefficient of q. Are you feeling overwhelmed? Well, there's a silly way to remember all of this. And it's this silly little phrase. You could even say that it's a name of some guy who just really likes rational functions, and we'll say he wears glasses, and I can say that because I wear glasses. So people that like rational functions wear glasses. And maybe his name is Bobobotinide. It's a cute name. His parents really gave him an easy time in life with that name. But here are what the letters stand for. If this is talking about exponents, in order to figure out the horizontal asymptotes. So if the exponents are bigger on bottom, this is like a 0 right here, then it's y equals 0. If they are bigger on top, then there's no horizontal asymptote. And I'm actually going to put a little note here. Check for a slant asymptote. We'll check that. We'll talk about that in a little bit. But if the degree is equal, then you'll divide the leading coefficients. So Bobobotinide, bigger on bottom, it's y equals 0. Bigger on top, there's no horizontal asymptote, but that's when you'll check for something else. And if the exponents are equal, divide the leading coefficient. So bigger on bottom would be something like x over x squared, or x minus 1 over x squared plus 3. Like, see how the exponent is bigger on the bottom. If it's bigger on the top, that could be something like x to the 4th over x minus 1. If it's bigger on the top, that means there'll be no horizontal asymptote. And if it's equal, you'll divide the leading coefficient. So if you had 2x cubed over x cubed plus 1, then you would divide the leading coefficient, so you divide the 2 divided by, there's a 1 right here, so that would be y equals 2. Okay, so that summarizes the table a little bit. I think it's much easier to remember that, and it's really easy to just jot those letters down, and then you remember all of the rules for getting the horizontal asymptote. Let's practice our knowledge here and use this function right here. Real quick, let's just go ahead and reward those who have watched this video. I would like for all of you to memorize what Bobobotinide means tonight, and then I'm going to quiz you on it tomorrow. Maybe not quiz, maybe bonus points. I don't know, we'll see. But I want all of you to memorize it and be ready to explain it to me tomorrow. Okay, so we've got f of x equals negative 3x plus 7 over x minus 2. Alright, so we can figure out, let's see, the numerator and the denominator have the same degree. So, remember with horizontal asymptotes, that's the Bobobotinide thing. So if I'm looking at if they are equal, that's the IED part, if they're equal, divide the leading coefficients. So we have negative 3 over, that's a 1x, so my horizontal asymptote is y equals negative 3. Once you know your horizontal asymptote, you also know the range, and that will be the set of all real numbers where y is not equal to negative 3. Okay, and let's see, also when written in the form that we currently see here, we can identify the x and the y-intercepts if they exist. Okay, so, you know what, before we do those, let's talk about the domain and vertical asymptote. I was going to skip it, but let's go ahead and do that now. So for the domain, it may be easier for you to think about finding the vertical asymptote first. So the vertical asymptote, you'll look at the denominator, figure out what would make that equal to 0, and so I have that x minus 2, so what would make that equal to 0? Well, that would be an x value of 2. So I have a vertical asymptote of x equal to 2, because if it were 2, I'd be dividing by 0. Don't want that. So the domain will be the set of all real numbers where x is not equal to 2. Okay, now let's identify the x and the y-intercepts if they exist. Why do I say if they exist? Well, it's possible that there are no x or y-intercepts. For example, think of that parent function that we just looked at a moment ago. It looked roughly like this, right? Well, it never crosses the x or the y-axis. So for 1 over x, it has no x or y-intercept. But for this one right here, x-intercepts, well, that will be when f of x is equal to 0. So a fraction is 0 when the numerator is 0. So if I take that numerator and I set it equal to 0 and solve, get negative 3x equals negative 7, so x equals 7/3. Then I found my x-intercepts. And remember, whenever graphing, the x-intercepts, the roots, and the zeros, that all means the same thing. So if you're asking for the zeros or the roots, finding the x-intercepts will do the same thing. But again, x-intercepts, you take the numerator and you set it equal to 0 and you solve for x. So to find the coordinate, I want to know the exact location for this point. You would take that 7/3, that's the x value, goes right here. And remember, this is an x-intercept, so that means it would be on the x-axis. That means its y value would be 0. So it's at 7/3, 0. For the y-intercept, remember that's when x is always equal to 0. So for this one, you just plug the 0 in for x. You'd have negative 3 times 0 plus 7 over 0 minus 2. And so you would get 7 over negative 2. So the coordinate for this one would be, the x is 0 since we plugged the 0 in, and the y value is negative 7/2. So just like we've mentioned, like with parabolas where we had vertex or transformation forms with a times x minus h squared plus k, where it's easy to see how it was stretched, moved to the left and right and up and down. In standard form, where we had ax squared plus bx plus c, rational functions can have two forms, just like we've practiced now. We've got this transformation form, and then we've got the quotient of two polynomials. So in this first one, it's really easy to just move the points around. On this second one, you have to hunt the information down a little bit, use bobobotinide and all of that to find it. But challenge is sometimes fun, right? Okay. Let's practice graphing the same function that we've been using. So we need to identify all of the parts first. So for the vertical asymptote, remember that's where the denominator is equal to 0. So if I set that equal to 0 and solve, I'll get that x equals 2. For the horizontal asymptote, that's the bobobotinide thing. So here my degree is equal. So if it's equal, I divide the leading coefficients. Negative 3 divided by 1 is negative 3. We found the x and the y-intercept, so we have the 7/3, 0, and the y-intercept was 0, negative 7/2. And the domain will match the vertical asymptote here, so it'll be the set of all real numbers where x is not equal to 2. And the range is going to be the set of all real numbers, and it will match the horizontal asymptote where y does not equal negative 3. So again, what I'm going to do is plot the asymptotes first and then go from there. So I'm going to use that blue color again. And I've got a vertical asymptote at 2, so that's x equals 2. Put in a squiggle line there. Okay, and then my horizontal asymptote is at y equals negative 3. So 1, 2, 3. Okay. So there are the asymptotes. Now previously, before we did the quotient of two polynomials, we pretended like this was the new origin and moved everything. But I can't just do that so easily because this is not in transformation form. So whenever it comes down to this, I know you're not going to be extremely excited about it, but it's not all that bad. We're going to pick some x values on each side of the vertical asymptote. We don't have to worry about the horizontal, but just on each side of the vertical asymptote. So for example, if we took f of 1. So I'm going to pick something to the left here. So if I pick f of 1, what happens when I plug in that 1? So I'd have negative 3 times 1 is negative 3, then I'll add 7 divided by 1 minus 2. So you'll end up with 4 over negative 1, and that equals negative 4. So the point will be at 1 negative 4. 1, 2, 3, 4. So there's our first point. We could pick negative 1. Oh, by the way, don't forget, we do know our x and our y-intercept, so let's go ahead and put those on. The y-intercept is at negative 7/2. So that's negative 1, 2, 3.5. Got a little bit close there. Okay. And then, so let's pick the next one over, negative 1. So f of negative 1. Plug that in. So negative 3 times negative 1 is 3. Add 7 over negative 1 minus 2. So I'll have 10 over negative 3. So that'll be negative 3 1/3. So at negative 1 it's negative 1, 2, 3 1/3. So it's kind of in this area. So it's sketching our hyperbola. When doing it this way, you only need to do 3 points on each side. So 1, 2, let's pick f of 3. And whenever we do that, we'll get negative 3 times 3 is negative 9, and then add 7 over 3 minus 2. So that is negative 2 over 1, which is negative 2. So we have 1, 2, 3, negative 2. Don't forget that we do have our x-intercept at 7/3, 0. So that's 2 1/3, 0. It's right there. And then we could also pick the point, how about we try 4, f of 4. There's no need to pick complicated points, just pick the easiest ones and the closest ones. So we've got f of 4, so that'll be negative 3 times 4 is negative 12, add 7 over 4 minus 2. So then we'll get negative 5 over 2, so negative 2.5. So at the point 4, negative 2.5. 1, 2, 3, 4, negative 2.5. So there's the other part of the hyperbola. And you'll always want to kind of reach towards, as you draw on the rest of it here, get it close to that asymptote. Don't necessarily draw on it, but just get close to it. And just since we're here, let's talk about this. Up until now, asymptotes, we haven't crossed them. We get close to them, but we don't cross them. But as it turns out, that's just as x is getting really big, it's going to be really close to that asymptote. But you can, and you will have some homework problems that will cross it briefly, but then stay really close to the asymptote. So for horizontal asymptotes, you can cross them. It's not extremely common. You can cross them, but it'll stay really close to the asymptote. I know it's a little bit strange, but it really has more to do with end behavior than it does right here at the middle of the graph. Okay, so let's go back to page 594 and read some of the information from the top of it. And we've got zeros and vertical asymptotes. So if we've got it set up as a quotient of two polynomials, and they're in standard form, and they've been factored and simplified completely, then the function f has zeros at each real value of x for p of x equal to 0. So it's going to say that you'll have zeros or roots or x-intercepts when you take your numerator, set it equal to 0, and solve for x. A vertical asymptote will be whenever the denominator is equal to 0. So zeros are when the numerator is equal to 0. The vertical asymptote is when the denominator is equal to 0. And it will take some practice getting used to knowing all of that and memorizing it. So let's just read through these examples that are right out of your book. If we were to identify the zeros and vertical asymptotes of f of x equals x squared minus 2x minus 3 all over x minus 2. First of all, factor everything to see if anything cancels. So our numerator factors into x plus 1 and x minus 3 over x minus 2. Well, nothing cancels out, and we will be doing that at some point in the future, probably tomorrow. But nothing cancels for now, and it's not that it was for naught that we did that, but we have made it easier to figure out the zeros, because the zeros are when the numerator equals 0. So if I set x plus 1 equal to 0, I'll get negative 1, x minus 3 equal to 0, I'll get positive 3. So we'll have zeros on the graph at negative 1 and 3. Vertical asymptotes will be when the denominator is equal to 0. So set it equal to 0, solve for x, and you get x equals 2. So zeros at negative 1 and 3, vertical asymptotes at 2. Now if we were to graph this function, Notice that we have a vertical asymptote because we solved for that at x equal to 2, and this graph is scaled by 2 right here. But going back to our original thing, and remember the horizontal asymptote, that's about the Bobo-Botnide thing. If it's bigger on top, there's no horizontal asymptote. So you'll see there's no horizontal asymptote. It doesn't have a boundary on those x values. So it would be, on the y values. So it would be all real numbers for the range. So then if we graph this function, then you could pick some points on each side of the vertical asymptote. This is what your graph would end up looking like. Let's look at a couple more examples. If you've got x squared plus x minus 6 over x, and we want to look at the zeros and the asymptotes, again, factor. The factors of the numerator set equal to 0. You'll get negative 3 and 2 as your zeros. For the denominator, set it equal to 0 and solve, and you get x equals 0. So here our vertical asymptote is 0. So for the horizontal asymptote, again, if it's bigger on top, there is no horizontal asymptote. It's that botan, B-O-T-N. And so there's no horizontal asymptote, so you would do your vertical asymptote, pick some points on each side, sketch it in. And then this one, x minus 1 over x squared. The 0 is taking the numerator equal to 0 and solving, so you get 1. Vertical asymptotes when the denominator is 0. So x squared equals 0 would give you x equals 0. Whenever it's bigger on the bottom, that's that first part, B-O, then that means it will have a horizontal asymptote of y equals 0. So you can see here there's the vertical asymptote, the horizontal asymptote, and the 0 is at 1, 0, which just so happens to be on the horizontal asymptote. And I told you before, you won't always see it, but sometimes you do cross the asymptote, and that's okay. We don't panic. It's just as x is getting bigger, it's going to stay really, really, really close to that asymptote, and it probably won't cross it again. But, well, it will not cross it again since we already found our 0. But it'll just stay really close to that asymptote as it goes on. So don't panic if you cross the asymptote. So we have one more example here. It's a little bit strange before we learn about one more thing. And let's do the same thing. So we take out the greatest common factor of 2, and you factor that x squared minus 1, that's a difference of 2 squares, and factor the denominator, which is a difference of 2 squares. You'll get your zeros of negative 1 and 1. From the numerator equal to 0. The asymptotes are negative 2 and 2 from the denominator equal to 0. Horizontal asymptote, that's the Bobo-Botnide. Here the degrees are equal, so we'll divide the leading coefficients. So 2 divided by 1 is 2. So vertical asymptotes, I've got 2 this time. So you can see in my graph here I have 2 vertical asymptotes. I do know my zeros are at negative 1 and 1. So there's my negative 1 and positive 1. So just like I did before, anytime I have a vertical asymptote, I want to pick points on each side of it so I can see what's kind of happening. So you'd pick a point over here, a couple in the middle, a couple over here, and then you'd be able to sketch in your graph. So you may see graphs like this as well. The possibilities are almost endless with these kind of graphs. You're going to see all kinds of different graphs with different personalities. But we need to talk about one more thing before we finish this up, and this is the last slide of information. So you can take a deep breath, but you need to pay attention. Some rational functions have a slant asymptote instead of a horizontal asymptote. Remember on the Bobo-Botnide, I said if it's bigger on top, there's no horizontal asymptote, but I put that little star SA, and that means to check for a slant asymptote. So rational function, it's really easy to tell that it has a slant asymptote. It will have a slant asymptote if the degree, that's supposed to be a D, degree of the numerator is exactly 1 degree greater than the degree of the denominator. So looking between the two, if the one on top is exactly 1 bigger than the bottom, so that's a 2 and this is a 1, if 2 is exactly bigger than 1, that means this will have a slant asymptote instead of a horizontal asymptote. So this would have a slant asymptote. So to find it, we're going to use synthetic division. You could use long division. Synthetic takes up less space. So that's what I'm going to use here. So remember this, minus 2, take the opposite sign here. So for the a value, that's 2. And then for the numerator, we want to put that into standard form and look at its coefficients. So this is 1x squared plus a positive 1x plus 0. There's nothing else on the end there. So you bring down the first term, multiply it by 2, and then add. 3 times 2 is 6, and then add. Get 6. So whenever you're doing synthetic division for these rational functions, you get to ignore the remainder. And you only look at this first part. So this is x to the first power, x to the 0 power. So we have y equals x plus 3. That's 1x plus 3. So let's fill in this information. For the vertical asymptote, we look at the denominator equal to 0. That will be x equals 2. Horizontal asymptote, bobobotinide. If it's bigger on top, there's no horizontal asymptote. Instead, we had a slant asymptote. And we've already found that it is at y equals x plus 3. The x-intercept, you need to look at the numerator, set it equal to 0. It's probably easier to factor it out first if you have x times x plus 1. When you set each of the factors equal to 0 and solve, you'll get x equal to 0. And then for the other one, x plus 1 equal to 0 solved, you'll get x equals -1. The y-intercept, remember you plug in 0 for the x's, so you'd have 0 squared is 0 plus 0 over 0 minus 2 is -2, so that's just equal to 0. So your y-intercept is at 0. The domain matches the vertical asymptote, so that's a set of all real numbers where x is not equal to 2. And the range will match the horizontal, but because we do not have a horizontal asymptote, when that happens, you can feel happy because you don't need to worry about it. So we're just not going to even worry about that for now. Because it would be a little bit technical in that you'd have to find the local maximum and minimum for it. We're not going to worry about that. So if, again, there is a slant asymptote instead of a horizontal, don't worry about the range. So just like we did before, let's go ahead and sketch in the asymptotes. So we've got a vertical asymptote at x equals 2. There it is. But we've got a slant asymptote at y equals x plus 3. So remember that would be at a y-intercept of 3. So 1, 2, 3. So we know it's going through there. And it has a positive slope of 1. So it'd be going like that. Okay? And then we would want to, whoa, got crazy. Okay. All better. Okay. Then we would want to pick some points on each side of the vertical asymptote. So we'll pick some, and then don't forget we do have the the x and y intercepts. So we've got x is 0 and -1. So we've got a x-intercept at 0, we've got an x-intercept at -1. We have a y-intercept at 0, well it's already there. So what we're going to do is let's try f of 1. Looks like an easy enough one. So f of 1, when we plug that in, back into our function here, we'd have 1 squared is 1 plus x is 1 over 1 minus 2. So you'll have 2 over -1, that's -2. So that's the point 1, -2. To figure out what's going on over here, let's go ahead and try f of -2. So -2 squared is 4, then plus a -2 all over -2 minus 2. So that's 2 over -4, or -1/2. So that's the point -2, -1/2. So I can see this side is just doing this sort of thing over here. Whoops. Let's do a little better job on that. Now it does go above that x-axis right there because it's a 0, or it's an x-intercept, so it'll go above it and then back down. But we need to figure out what's going on this other side. So let's try f of 3. And when we plug in 3, so 3 squared is 9 plus 3 over 3 minus 2. So we get 12 over 1, which is 12. So we have the point 3, 12. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let's do one more. How about f of 4? 4 squared is 16 plus 4 over 4 minus 2. So that's 20 over 2. That's equal to 10. So we have the point 1, 2, 3, 4, and then 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's just about enough. Let's go ahead and sketch that in, going back towards the asymptotes. And that's it. You should feel incredibly proud of yourself if you were able to handle that. We're going to practice one more example like this in class. And if you want to get a head start on it, here it is. So again, you want to find the vertical, horizontal asymptotes or slant asymptotes if there is one, x and y intercepts, and graph. All right, I'll see you in class. I know you have questions. Jot them down so you don't forget about them, and I'll see you later. Bye.